There it goes. So, for the second part of section 6, we're looking at just slant asymptotes. Now, these show up when you don't have horizontal asymptotes. Not every time, but fairly often. Because the idea of a slant asymptote, or what they also call an oblique asymptote, it happens whenever the degree of the numerator is exactly one more than the degree of the denominator. So the degree of the numerator is bigger than the denominator, so like this one, we had no horizontal asymptote there. Okay, because if you look at this, x squared is bigger than x, degree-wise. So this one doesn't have a horizontal asymptote, but it does end up having a slant asymptote. Now, that slant asymptote, the way we're going to generate that is to, well, modify the equation. Now, what ends up happening here, because the top's bigger than the bottom, what we do is actually divide those two things. It's a division problem, right? We rewrite it into a different format so that we can see what it's made out of. Well, this thing, when you divide it, you get x minus 2 as a quotient. Your remainder is 2. So it's x minus 2 plus 2 over that x plus 1. Now I can do the same process as I did for the horizontal asymptotes. If you made x gigantic, what's going to happen to this fraction?
Small.
It's going to become irrelevant. It's going to become infinitesimal. So all that's left is, behavior-wise, for really large values of x, since this becomes irrelevant, you end up with just x minus 2. Your quotient ends up being that slant asymptote. Because what's going on is you make x gigantic, it's going to approach that line that would have been there for x minus 2. Okay? Does that make sense? So it makes that not too hard to figure out. If I want to sketch this graph, I'm going to go through the exact same process as before. What would the y-intercept be? Yeah, it doesn't have one. There isn't one. Because if I plug in 0, I'm dividing by 0. It doesn't exist. X-intercept. How do I find x-intercept again? Set the y equal to 0. In other words, set the numerator equal to 0. So in this case, I have 3x squared plus 1 equals 0. Then what? Do what? Subtract the 1, so I have 3x squared equals 1, negative 1. Divide by 3. Anybody see a problem yet? Yeah, it's a square root of a negative. So what's that mean? There are no x-intercepts. Okay? So, what's next? Asymptotes. Vertical asymptotes. Do I have any vertical asymptotes? Where? At x equals 0. That's when the denominator equals 0. What about horizontal asymptotes? Horizontal asymptotes? None of them. The reason is, anytime you have a slant asymptote, you're not going to have any horizontal asymptotes. Guaranteed, because the top's going to be bigger than the bottom. So I do have a slant asymptote. Now for this I need to do some work. The reason I have a slant asymptote is the degree of the numerator is exactly 1 bigger than the degree of the denominator. Okay? So that means when I divide them, if I take x into 3x squared plus 0x plus 1, well, what do I multiply x by to get 3x squared? 3x. So that gives me 3x squared. Subtract those, I get 0. Bring down the 0. I have 0. So then bring down the 1. Your remainder is what? 1. Yeah, obviously don't bother writing the plus 0 part of it, but you have a remainder of 1. So with that, that gives me 3x plus 1 over what? X. Now what I want to do is look at this and think about what happens. What's this thing behave like if x is gigantic? Well, if x is gigantic, this becomes pointless. But the 3x it just starts acting like as if it was 3 times a gigantic number, or really negative number. So your slant asymptote is just this. So now when I go to graph this, I'm going to put in the asymptotes. One of the asymptotes is the y-axis. Okay? The slant asymptote is the line y equals 3x. So I'm going to go over 3 up 1, or I said that backwards, up 3 over 1, up 3 over 1, so on and so forth. Now the question is, I treat it the same way as if I had a horizontal asymptote. If I look to the right of this asymptote here, am I going to graph below the slant asymptote or above it? How do you know? Because there's no x-intercepts, exactly. So it looks like this. Down here, same reason, it's going to be here. Okay, and if I graph this on the calculator, you should be able to see that you get that type of graph, but it also allows you to real quickly see what happens at those huge values. Now the really downside of these slant asymptotes is that the calculator can't really kind of hand them to you. The horizontal asymptotes, they can kind of give it to you. If you put in gigantic values, you can kind of figure out what it is without actually knowing that simplification process. Honestly, it's easier to just simplify, but whatever. So looking at this, that's pretty much the same graph. Well, if I just zoom and do zoom out, you actually start to lose visual on that asymptote, the vertical one. And it ends up looking a lot like the line y equals 3x. And that's the idea. At the extreme values, it ends up essentially acting exactly like y equals 3x. It's infinitesimally close technically, but if I graph y equals 3x, you won't be able to tell a difference at the extreme. You literally see the red line go right over top.
Why is it like?
Why is what? Because I'm zoomed out so much that that part that locally is basically smashed so flat you can't tell the difference between it and the y-axis. But if I zoom back in, it's going to take forever to process. That's going to do too much. Anyway, you zoom back in, you can start seeing the lines. Questions on that?
It happened to mine one time.
Yeah, second and on stops it, but yeah, doesn't matter. The window's not even that big. Here, I'll just do zoom standard. Yeah, second and on pauses it. Yeah.
No, you press enter. Like in the corner, it's usually yellow spinning, but it's like white when you press enter. Before it, like,
Oh, that pauses it?
Yeah.
Ah, I did not know that. Okay. So I tried to. Okay, I see what happened then. But you can see it locally. Okay. Let's look at a couple other things real quick. For this, there's one of these rational functions. The cost C in millions of dollars for removing P% of the industrial pollutants is discharged into a river is given by that rational function. The proposed new law would require companies to remove 80% of their pollutants discharged into the river. The current law requires 45% removal. How much additional cost would the companies incur as a result of this law? So what would you do? What would you plug in? 80 and 45? Now you'd actually do 80 and the 45 because it designates P%. So P is whatever number's in front of the percent sign. So that's one that can throw you a little bit. You do actually use 80 and 45 in this one because of the way it's written. Okay, it's a formula designed to be used that way. So in other words, you're going to do C of 80 and C of 45. Go ahead and find those two for me. Anybody else get that?
Yeah.
What about for 45?
200.
What did you say it was?
208.64.
208.6. 3 repeating. But anyway, now, what's the cost to the companies? What do you do with those? Subtract. What do you get?
811.36.
811 what? It's only going to cost me $811? Million.
Oh, wow.
811 million. Okay. Now, think about the behavior of this graph. It has asymptotes. Oh, what's the vertical asymptote it has? 100. Because logically, could you ever actually reach 100%? No. Are there any horizontal asymptotes?
No, because the top value is one greater than that.
Horizontal, not slant. Where's the horizontal asymptote? Careful. Because you throw out any constant, right? And just look at the biggest degree term. It'd be negative what? 255. Because 255p divided by negative p. So it's negative 255. So the idea is, and it looks a little bit strange, but if I graph this thing from 0 to 100, because negative values wouldn't make any sense, and I know I want to go up to, well, at least 811, right? So I'd probably go up to 1,000. Whoops. And graph that. You can see the rise, the first 40% isn't that much. For 40, you have about or 45, not 40, sorry. 45, you have that 208. Not 80, you have 1,020. So it's 811 million increase from 45 to 80. But what about from 80 to 90? What is it from 80 to 90? What did you get when you put in 90? Yeah, 2,000. So from that next 10%, so the idea here, this 35% costs an extra $811 million. The next 10% costs another $1 billion. 1,000 million, right? Why? Either math or just logically. Why does that cost an extra $1 billion to go up 10% when it only costs 800 million to go up 35%? Yeah.
Because eventually you get to the point where purifying the air anymore becomes extremely difficult. Plus, there's different amounts of things in the air, and you can purify one without purifying the other, making it easier to purify the easier ones than it would be to purify everything.
Everything that's left. We're talking about water, but same principle, yeah. The idea, the bigger stuff's easier to take out, so you end up with that smaller and smaller remainder. Mathematically, why? Not the horizontal asymptote, the vertical asymptote's causing the problem. Because as you get closer and closer to this thing, if I put in 99%, you're up at 25,000 there. Or not 25,000, but 25 billion. Right? Even down to 98, it starts doubling every percent. If you go up 99.5, you're up to 50. 99.9, 254 billion. So you ever going to reach 100%? Probably not. Okay. One more. A rectangular page is designed to contain 57 square inches of print. the margins on each side, as well as the top and the bottom, are 1 inch deep. What should the dimension of the page be in order to use the least amount of paper? This one takes a little bit of thought. First off, this is a rectangular page, right?
Yeah.
And you're talking about I want to minimize the dimensions or the amount of paper used. So what type of measurement is that? Is it length? Is it volume? Is it what?
Light.
Area.
Oh,
For the page, you're trying to minimize the amount of area, the amount of paper used, right? What's the formula for area of a rectangle? Length times width. I didn't hear you. Length times width for that. So, the problem is I got these margins to deal with. Length minus 2 and width minus 2. The problem is the 57 I have, is that based with those inches in there or not? No. It's just the print area. The thing that's locked in that I can't not reduce or increase is that print area. It's 57 square inches, right? So I want to set up actually two different problems. 57 is going to be equal to, and I would do either base times height, or you could do length and width again. Just realize that's not the same as this length and width here. Because these ones I need to then modify a little bit. This is for the area of the print. How much bigger is the area of the page going to be than the area of the print? Length and width wise. Well, yeah, but what would I write here? What would I multiply to get the area of the page compared to the area of the print? Yeah, you're adding 4, right, overall, but you were thinking linear mixed with area. I would just describe it as doing what to the length and what to the width. Yeah, adding 2 to each. So when you compare the print to the page, this is how your area formulas line up. Because length times width gives you the 57 for the print, then you need to tack on an inch on each side, top and bottom, left and right. Okay? Now I want to minimize this area number, right? So I'm going to create a formula that then I can find the minimum of. But the problem is, I need a of just one thing for a function. I can't have a of L and W at the same time. So what do I do?
Put in one variable.
Yeah.
Say again? I can't hear you. Yeah, go over here, redefine this as one variable equals something else. So if I divide by L, that's going to give me W is equal to 57 over L. Then go back over here and just define things in terms of L. Because here I have L plus 2 times what? 57 over L plus 2. That now I can find the minimum of. At this point, though, I'd be a little bit lazy and just graph it on the calculator. Go ahead and graph that equation. Find your minimum. What's your minimum?
Equals 7.5, and the area is 7.
Anybody else get that? Is anybody in the graph? That's kind of weird. You got to look at your limitations. When you graph it, make sure you go up far enough that you can actually see it. And you said that minimum was 50 or no 7.55,
Yeah,
and what was that minimum area?
91.1.
So the idea is the graph doesn't even really start until that lowest point of 91. So you got to go up to more than 100 to be able to even see the bottom of the graph. And that's going to just take kind of playing around with the window a little bit. Okay? Anyway, once you have that, or you could go to the table, see your values, and then mess with your window from there. What does that mean? What's my answer?
Well, you have to solve for W.
Yeah, you have to solve for W first, so plug that in. What's 57 divided by 7.55?
7.54.
7.55?
Yeah.
It's a square. Happens a lot. That's why when you start getting to more later on this year and then in AP Calc, they start putting other limitations. Because the thing is, when you're usually trying to either maximize or minimize, you usually end up with either a circle or a square, depending on the limitations. So they start giving you more limitations on top of that. They'll lock in one side so it can't be a square. Things like that. So what's my answer then? What's the answer? Nope. What? Yeah, the dimensions of the paper is 9.55 by 9.55. Questions on any of it? Okay. The rest of the time is yours.